Okay, wonderful. Welcome. We have over 75 people with us today. This is great. Welcome to the Conservation Impact Evaluation and Implementation Science Seminar Series. I'm Sheila Reddy, and together with Rachel Martin of Conservation X Labs and Seb Costado of Conservation International, we are hosting this session today. We have an absolute all-star lineup of speakers sharing their insights each month, and it's always on the first Tuesday of the month. So this seminar series is an activity of the Impact Evaluation Working Group. This is one of the newest working groups of the Society for Conservation Biology. And we've got some great news. Thanks to 100 people who offered their signature in support of the working group, we're now in the process of applying for full status. This is great. Thank you. So what is the aim of the working group? In a nutshell, it is to support evidence-based conservation, and doing so by advancing the use of counterfactual approaches to impact evaluation. So please take a chance to learn more about the group by checking out the website, engaging with us on Twitter, or signing up for the email list. So before we get started today, let me just make a few housekeeping notes. The general approach to the session today is that we'll start with a speaker, followed by what is usually a really robust question and answer session. I want to note that for the question and answer session, you post your questions in the chat, and those questions will be summarized by Seb to the speaker. You can't unmute yourself or raise your hand. Please also, if you find it helpful, take advantage of the live transcription function on Zoom. It's really fantastic. As always, the seminar will be recorded and we'll share it on the Vimeo channel. And please engage with us on social media. Use the hashtag Tuesdays with Teamcounterfactual and tag @IDoImpact. So with that, please join me in welcoming Kathy Baylis from University of California, Santa Barbara. Today, Kathy will be talking about predicting deforestation with neural networks. Over to you, Kathy.
Great. Thanks so much. Thanks, Sheila. Thanks, everybody, for joining me. Just a second. So let me try and share my screen and oops. Let me start from the beginning. Maybe that would help. Hold on. This is what happens when we do a test run beforehand and I forget to go back to the first slide. So thanks for joining me. My name is Kathy Baylis. I'm a professor of geography at University of California, Santa Barbara. And what I want to talk to you today about is really an idea more than a specific model. And that's just the idea of, is it possible to use machine learning, some of these machine learning algorithms to do a better job of predicting where and when deforestation is going to happen? Now, there's a whole bunch of reasons why we might want to do that. I don't think anybody on this call is everyone's probably very aware of why we might care about these things. I mean, we might want to know just generally where deforestation is likely to happen for targeting interventions, for targeting monitoring, that kind of thing. We might also want to have some measure of the possible deforestation pressure going forward. And obviously, there's lots of people actively working on this to try and develop measures of additionality of various conservation programs. And my particular interest is really having some predictions of deforestation in the purpose of impact evaluation. So again, I appreciated the fact that this tagline for this group is Team Counterfactual, but very much here I'm trying to tee up a model that can predict counterfactual levels of deforestation so we can evaluate the effect of conservation programs. Also, well known to everybody on in this room, impact evaluation and conservation programs is quite often very tricky, largely because these are interventions that are not randomly allocated over space. And there's a lot of treatment heterogeneity as well. And so, I mean, we've seen a flurry of attempts to try and deal with this through, things like differences with matched treatment and controls, synthetic controls, various versions now of synthetic controls, as well as kind of many other methods, people using regression discontinuity in some cases. So we're all trying to find ways to get at this, to be able to evaluate the intervention, evaluate conservation interventions. And I'm going to try and pitch that maybe we can help, maybe machine learning can help here. So I should note this is very, very preliminary work. So I just want to present you kind of where we're at so far. And hopefully I'll convince you that this is an idea worth pursuing, but at no means I'm going to try to convince you that we're there yet. So what we're going to do here is we're trying to develop a proof of concept where we're using neural networks to predict deforestation. We're focusing in on the Amazon, and we started off doing sort of a relatively simple version of a neural network, just looking at sort of a cross-sectional set of data. So using 2000 data to predict sort of cumulative deforestation between 2000 and 2014. And I'll try to convince you that that looks reasonable. Some of the results we're getting there seem to be pretty decent. And so then that led us to try and apply methods that are more geared towards panel or longitudinal data. So that are trying to sort of take into account diffusion of deforestation over time. In particular, we're going to use a recurrent neural network. And so what we're going to do, and this is what I'll spend most of my time on this morning, is to try and show you how this model sort of takes data, including all the time series data from 2000 to 2010, and tries to sort of forecast deforestation between 2011 to 2014. So we're going to do that. We're going to compare that against sort of a very simple OLS kind of model that mimics that recurrent neural network structure. This is nothing any normal person would run ever. The only reason we do it is really to try and kind of understand better what is the infrastructure of the recurrent neural network and sort of what is it capturing. And then we use a very standard sort of dynamic panel kind of model. These are both totally straw people. So again, I mean, these are not the world's best models that we're comparing our neural network against, and I'm not going to pretend that they are, but I think it is informative just to kind of think about some bog standard ways that we go about these things and how they compare to what we're seeing. Punchline is that it's working-ish. We're not getting perfect fits by any stretch, but it's not bad. The one caveat so far is that the recurrent neural network isn't so far seeming to do that much better than just our simple cross-sectional method, and so that there's a lot to explore there. We want to better understand sort of how to make it better, and I think so again, very preliminary, but this is kind of where we're at. All right. So why on earth would we want to do this? Well, so one thing that is, again, I think obvious to everybody in this room is that, I mean, the drivers of deforestation are probably very nonlinear and probably very heterogeneous. So you can imagine there's like going to be lots of threshold effects that a linear model might not capture. So you might see deforestation up to 2000 meters in elevation, but none after that. So it's not quite often, say, you wouldn't expect deforestation to be linearly related to elevation. We also might expect that you would have like the effect of elevation be very different at different elevations. You also might expect that sort of, for example, a 1 kilometer increase in distance to road could have a very different effect if you're close to a town or close to versus if you're in the middle of a swamp, right? So there's going to be lots and lots of interaction effects. We could build that into a standard linear kind of regression model by just throwing in more and more interaction effects and more higher order measures. So, elevation squared, elevation cubed, et cetera, et cetera. But at some point, it becomes a bit of a mess. And the nice thing is that neural networks can actually help us kind of uncover some of those patterns instead of us having to sort of guess at them and to put them into our model. It also, one thing that we don't make use of here yet, but I just want to sort of dangle it in front of you as a possible benefit, is that you can also, it's very easy to design neural networks to try and predict multiple outcomes simultaneously. So say if you wanted to predict not only deforestation, but reforestation, you could do that, which I think could be cool. So apologies for the many people in the crowd that are comfortable already with neural networks. I just want to spend a couple minutes on this mostly because as somebody coming from more the applied economics side of things, this was all new to me. So I'm going to drag you along through my learning process a bit here. So neural networks, basically, the idea is you've got you've got an input layer, and that's just like our standard set of input data that we would use in a regression, right? Our standard sort of covariates. And then you've basically got your output layer, which is the things we're trying to predict. In this case, deforestation. Again, it can be multi-dimensional, so we could be trying to predict deforestation and say reforestation. And then you've got these quote unquote hidden layers that are transforming those input data to the output. Now, in the world's simplest neural network, there in the middle, if you have no hidden layer, this could look an awful lot like a standard regression. So if we're directly sort of transforming our input data to our output data, and if you're doing that using a linear transformation, that gets back to standard linear regression. So just trying to convince you that everybody who's run a linear regression has run a neural network. Same thing if you have a sigmoid function instead of a linear function between these things, you're essentially running a logit. The big difference with neural networks is that they've got sort of a bunch more layers in between usually. People probably heard about deep networks. Deep networks imply there are multiple hidden layers in the middle there. And the idea of each of those hidden layers is basically computing weights on the data that are being fed into that layer. So if you think about like in terms of a standard regression, those weights would be like our standard beta coefficients. Then it's also adding adding a constant. So again, notice this middle bit is just like a standard linear regression, but then it's taking some transformation of that. If this can be just linear, get back to linear regression, or this could be something like trying to transform it into, again, the sigmoid function, that kind of thing. Okay, so that's what's happening at each layer. So each layer is taking the input from the layer before, transforming it, feeding it forward, transforming it, feeding it forward, etc. Okay, and you can choose how many layers, how many nodes, blah, blah, blah. The nice thing is the nice thing about that is that it's automatically allowing for all sorts of interactions between and higher order effects of all of our input data. So if it's picking up that what really matters is interacting potential value, property value, agricultural value of the property in agricultural revenue and distance to road with elevation, it should be able to pick that up. There's a bunch of different activation functions you can use in here, and then that was that little sigma that we saw before. So just to kind of tee things up, here's what we tried out first, which was just a simple cross section. And what we did here was and by simple cross-sectional neural network, I really mean simple. We only have 3 hidden layers, which is small in these things. And we used a linear activation in the last layer, which is just like an ordinary least squares regression. And the reason we did that is we wanted this model to be able to capture, to nest the standard linear regression we're going to compare it to. We train up this model using, and I'll go into this in more detail on sort of our trained data set versus, and then we compare it to our validation set, and as you can see, there is a little bit of a gap here between the two, which suggests that we're doing
that our model might be overfitting slightly, and by that I mean it's we're picking up a lot of information from our training data that aren't necessarily following over to our validation data, but it's behaving pretty well. The model essentially we're looking at is again trying to predict the sum of deforestation between 2014 and 2014 as a function of sort of standard stuff in terms of baseline forest cover, travel time to a bunch of things like ports, cities, a bunch of other characteristics, elevation, long, slope, etc. Potential agricultural revenue, which we take by looking at international prices times potential yield, and sort of weighted by the average harvested area in that agroecological zone. Okay, we standardize all variables, and just to give you the punchline here, so here's the model that's running that same regression, just using an OLS, get an R-squared of about 0.39, 0.4, versus the neural network is doing a fair bit better. You know, okay, that hopefully that's convincing you that it's, you know, not horrid. This was what I found really striking. So here are those predictions mapped out against what we actually see. So on the left here is the total deforestation that we're seeing. In here specifically, we started with just Peru and Brazil, versus a linear prediction there in the standard linear model in the middle. As you can see, it's sort of not picking up the spatial nuance that the neural network is, which, you know, is good, because I mean that's something that neural networks should be good at doing, is kind of picking up that spatial heterogeneity. But it looks like it is compared to our OLS regression. So that's where we started. Next thing we wanted to try and do is, all right, now let's actually make use of the fact that we have time series data and sort of build a model that's actually using that information. There's several different architectures of neural nets that can take sort of that panel structure into account. One of them is called a recurrent neural network, or RNN, with long-term, short-term memory cells. And so basically the idea here is that it's taking information, taking your time series information and sort of filtering it through to predict sort of each step along the way. So it's using some time series data from last year to predict sort of deforestation this year, and then sort of feeding that information forward. The kind of effectively what's happening is it's a process of trying to figure out what information it needs to retain, i.e. does it need to retain what's happened 10 years ago, and what information can it forget? What's nice about that is that it basically means that you don't have to tell it what the time series structure is. So unlike sort of our standard models, which will impose some kind of autoregressive structure, i.e. things depend mostly on last year and maybe a little less on the year before, and they don't, you know, what happened 5 years ago really doesn't matter. Here, this will pick that up on its own, and it'll pick up sort of different temporal patterns for your different variables, both in terms of outcomes and your input data. So you don't need to specify that kind of lag structure. And again, it can vary. And that can be important because sometimes what might matter isn't necessarily just what happened last year. Maybe what really happens was that there was a road built, you know, 20 kilometers away 5 years ago, et cetera. So anyway, it's more flexible in terms of picking up that temporal information, but it also can pick up the spatial information as sort of a standard neural network. I'm going to run through this pretty quickly. Basically, we're using the same variables to a large part, except we're adding in some spatial lags of deforestation here. And the difference in some ways of what we're trying to do now is we're trying to use data from 2001 to 2010 to forecast forward annual deforestation from 2011 to 2015. essentially, there's, for folks who, well, there's 4 branches in this recurrent neural network structure. So each of our input vectors that have time series are its own branch. So that includes like past deforestation, spatially lagged deforestation, agricultural revenue, and then we feed in a bunch of the stuff that doesn't change over time. And for comparison, we compare this to a sort of just a standard dynamic panel model where we're looking at deforestation as a function of deforestation in the prior period and deforestation nearby in the prior period. But we also, again, mostly this is just as a thought experiment. We also try to sort of set up the data in a way that is sort of reflective of the way that the recurrent neural network treats it. So here we were trying to predict, again, deforestation from 2011 to 2015, but we're feeding in literally all lags of deforestation, all lags of spatial lags of deforestation, all prior revenue, et cetera, and just sort of being very naive and kind of dumping it all in there and see if the model will sort it out. We expanded our data here a little bit to include Colombia, Ecuador, and Bolivia, along with Peru and Brazil. And we're trying to, again, explain total deforestation. We're using the Hansen data. We're using the sort of the covariates that I mentioned before in terms of tree cover, travel time, elevation, slope, distance to river. The only thing here that's sort of maybe slightly different than the usual set is again, this potential agricultural revenue. Our grids, we're using a 9K by 9K grid cell, which is pretty big. We want to play around with that a little bit later. Anyway, that's kind of where we're at. Here's just to give you a sense of the data. So we've got, so this just is sort of looking at correlation, standard correlation coefficients, but you also get a sense of the distribution of some of our variables. And again, the variable we're trying to predict is that last one, so deforestation from 2011 to 2015. The correlations kind of make sense in terms of things like travel time tends to be negatively correlated with deforestation. Things like agricultural revenue seem to be positively correlated with deforestation. So, you know, it's kind of, anyway, it seems like the variables we're adding are coming in ways we might expect, or at least are correlated in ways we might expect. Now, one thing that we don't do usually in regression models is doing this train test split. So I want to take just a second to talk about that for folks who haven't run across this before. Because machine learning models are very flexible, we worry a lot about them learning too much from the data that they're trained on and not being generalizable. So for example, if you trained it on a bunch of data and you just gave it a lot of freedom and it found that, you know, there's a landowner named Fred who deforested all of their land, it might well learn that all landowners named Fred deforest all their land, which is probably not a generalizable thing you'd want it to learn. And so to deal with that, what we usually do is we train it on a subset of the data and then check it against other sets of the data to sort of see how well that model we trained here fits. Okay, explicitly that's the sort of the test, what's known as the train test split. Because there's a bunch of parameters we want to try and fit for the model, we also have this intermediate step, which is called the validation set. So basically we're training the initial model on the trained set of data, which is that sort of beigey green. And then we're trying to tune the model based on the sort of pink validation set. And we don't even look at the test set until we're done with the model. And we use the test set just to see how well it actually works. Because of concerns about spatial correlation, we, instead of doing samples pixel by pixel or grid cell by grid cell, we're basically using these 100K by 100K blocks as our split. So that the idea is that we're not sort of training the data on one grid cell and then testing it against the neighboring grid cell, which is going to have a very similar pattern and would tend to tell us we have a much better fit than we actually do. Okay. So we also compare this against, again, our panel regression. I'm just gonna skip that. For model fit, as I mentioned before, we basically have these 4 branches, 3 of which are sort of time series data, and the 4th of which is sort of our time invariant stuff. We see a pretty, sort of the blue line here is again tracing out sort of the root mean squared error, sort of fit on our training data, versus the orange line is tracing out sort of the fit on our validation data. And so long story short, you can see sort of a rapid improvement in both, but then it sort of flattens out after we get to about, well, 75 epochs. Okay, so punchline. Or beginning of the punchline. So here's just sort of it's a quick scatter plot in terms of what we're seeing in terms of deforestation. This is the first one is our sort of pseudo neural network model using the OLS. So again, we would not expect this to perform particularly well, and gee, it doesn't. We did this again largely just to kind of think through the data structure that the neural network uses and see if we can replicate that with a OLS model. More standard approach would be the dynamic panel model, and that's getting again an R-squared of about 0.447. Our neural network's doing a bit better than that. Notably, it's again not doing that much better than our cross-sectional neural network from before. Here again is just sort of maps of those predictions. So the true deforestation is on the left. The predictions from our 2 sort of OLS models, sort of including the panel OLS model, are on the right, in the middle and the right. And as you can tell, it's missing a whole bunch of mid-level deforestation. And in fact, it's not clear, but the red dots where it's predicting deforestation, it's predicting a huge amount of deforestation. So it's not capturing the spatial patterns. On the other hand, the neural network is doing a much better job. So that's the neural network's predictions again versus a standard panel model. And again, just eyeballing it, it looks like it's picking up a lot more of a spatial pattern than the panel. We've started to try and poke, inside the black box to look at the features and how they're affecting our deforestation. And so we're using Shapley values here. To be transparent, this is a Shapley values from our cross-sectional model, because we were fighting with that, getting it to work with our the recurrent neural network. I just want to sort of highlight this as something that's really useful to do in some of these neural network models, to kind of just gut check to make sure things are affecting the model predictions the way we'd expect. So just to highlight that, if you look at like the travel time to ports, so where you've got high values of travel time to ports, we tend to have less deforestation, kind of as you'd expect, right? Versus the blue is where we have low travel time to ports, i.e. it's close to ports and much higher deforestation. Similarly, for mean revenue, it's coming in the way you'd expect. But we also see lots of heterogeneity. So for example, like initial tree cover, where there's very little initial tree cover, there's very little deforestation, so there's not much to deforest. But in places with high tree cover, you see some of them have lots of deforestation, some of them have little deforestation, which I mean is kind of what we would probably expect. Some of those might be just very inaccessible places, some of them over here might be more accessible. The point of this though is that this is a kind of heterogeneity these neural network models can pick up quite easily without us having to put in a whole bunch of interaction terms. Okay. Just to kind of wrap up here, we checked our predictions in areas that become protected over our time frame versus don't, and we're getting worse fits for places that become protected. That's a little bit disconcerting because we're training the model sort of naively on places that are both become protected and don't. And so whether it's just doing a better job of learning from places that aren't protected, or just that that's the bulk of the data. I'm not sure quite why this is happening, but so far our predictions in the areas that get protected aren't quite as good. So we sort of want to worry about that or think about that if we want to take this to counterfactual prediction, which is where we want to go next. This is something probably everybody in this room knows, that many of you know better than I do. So obviously in the Amazon, there's been a whole bunch of protected areas come in since 2001. What we really want to do is take this model and then try and predict, use the data from before protection to try and forecast essentially places, the deforestation rates in places that were protected versus not, and compare the two to try and get a measure of the effect of protection. There's things we need to consider. There's all the standard two-way fixed effects concerns that they would apply here too, in that we would expect a lot of treatment heterogeneity, and we have a rollout. So we want to try and consider different cohorts and make sure, you know, the same kind of things that you do in the standard Callaway-Santana approach. We probably want to take that into account here with the machine learning stuff. We want to probably take this to biomass data so we can go a little bit back, so we have a little more data before some of those protected areas come in. And again, it would be nice to also take other kinds of land tenure regimes into account. But the nice thing is that the building block here that we're trying to pitch is that with a relatively flexible model here, hopefully we can use that to forecast deforestation over a number of different settings. So conclusions, which I'm hesitant to call conclusions because this is so preliminary, but hopefully I've convinced you that this is a useful thing to pursue, that these neural networks have the potential to be able to predict deforestation maybe better than some of our traditional methods. And in particular, they seem to be able to pick up spatial patterns and pick up heterogeneity, which is important if we care about predicting counterfactuals. That said, there's lots of caveats. We want to better understand the places where these models are working well and where they aren't. And so before we sort of take this to sort of a causal place. But once we do that, then I think I'm keen to try actually again predict using sort of some of the prior data and control data to predict sort of how well things like protected area statuses are working to limit deforestation. That's it. And again, apologies that this is quite so preliminary, but I wanted to kind of give you a sense of things that we're thinking about and get your feedback and input.
Fantastic. Thank you so much, Kathy. And no problem at all of presenting preliminary things, because it seems like you are one of the pioneers going to that space. So it's very good to see, you know, early on new trends and new ways of working with data and making the best of all the amazing data sets and machine learning algorithm that exist. As a starter, just to clarify some non-asked question, but that may be interesting at a very intuitive level. Is there major differences between the workflow when working with machine learning algorithm as opposed to more, you know, I would say the classic statistics, econometrics workflow? Would I say there's something different so people can map?
Yeah, no, that's a great question. So I mean, the big thing is again this train test split idea, and therefore thinking hard about what that needs to look like, which is something that those of us who, you know, are used to just happily running regressions aren't used to thinking about. So for example, we might we want those train and test blocks to be to not have too much correlation between them. Otherwise, we're going to kind of cheat when we're comparing our model to see how well it works in a test set, if our test set is basically the same as our training set. So again, this is something we just don't tend to think about. And all of this is because of this concern about overfitting. which is something we usually, in a standard linear regression approach, we just assume that by imposing linearity and not throwing in too many features or variables, control variables that we don't have to worry about overfitting. But it's actually, again, we can overfit with a regression model too. We just tend to kind of ignore that.
Okay. Oh, thanks. And there is a very similar question from someone in the audience that asks, you mentioned seeing a lot of things you may expect from the output and feature values, but is there anything you did not expect or that you don't believe you may have understood as well if you did not use neural network?
That's a, yeah. That's a great question. There were some aspects of the heterogeneity that are that I don't know if it's a question of whether we didn't expect it, but more that just we really need to explore a lot more. And that's the sort of the blessing and the curse of the neural networks, is because it's embedding a whole bunch of kind of nonlinearities, interaction effects, is sort of trying to unpack that takes a little more time. I think one thing I want to see, for example, is how well it's picking up new locations of deforestation. So I think it's capturing some of the diffusion reasonably well. So if you've got deforestation before, you know, the diffusion patterns it's picking up, but if you see a whole new deforestation area sort of pop up, that's one thing we want to do, is kind of see how well it's doing there. Yeah.
Okay, no, thank you. And probably on that, on the more level of the interpretation and unexpected things, someone asked a question: if why in your presentation you show that positive longitude seems to have a positive effect on deforestation? So do you have an explanation for that?
No,
no,
that I don't.
but can you explain the logic of having longitude as
yeah, why we put it in there, it's really to kind of help. So this was really for the machine learning model, and it's to help it pick up spatial patterns essentially. And because we had it in the machine learning model, we also put it in the regression model, whereas normally we wouldn't do that. It helped a fair bit in terms of the model. It definitely, the model fit improved a fair bit once we did throw in lat and lon. So the neural network was definitely making use of that. However, we also double checked to make sure it wasn't driving everything. So we also ran the machine learning model only on lat and lon, because in sort of past work, we've found that sometimes it can end up sort of only using lat and lon and sort of then driving everything from that. And thankfully it was not. So yeah, it mattered, but it didn't drive everything, which is good.
Interesting. Okay, so now I will have a series of questions that's probably more specific on the techniques and some comparison of models, and then we will transition towards links with impact evaluations. So just a question. Someone asked what the training partition size. You explained that you have the training, testing, and validation.
Yeah, so we've got, so I think it's 60, 20, 20 in terms of the percents, and then again, then we use those 100K blocks that again just to try and deal with spatial correlation.
Okay, and can you elaborate more on the 20K by 20K block split? People were some people.
So this is the 100K by 100K, yeah, block splits, and so the idea here this was from some earlier work where we just looked at a semi-variogram in terms of spatial spillovers in terms of deforestation, and we were finding that decayed pretty substantially, like the spatial correlation decayed pretty substantially in about 100K. So that's why we chose that block size, is we thought that would kind of reduce the amount of spatial correlation. And again, just the intuition here is sort of take an example of, imagine we were looking at sort of 1K by 1K grid cells, and say it just happened to be that our training set was right next to, like, was completely interspersed with our test set. the worry there would be that by training a model on our training data, and if our training data are basically correlated with, say, 0.99 degree of correlation with the test set, we don't really have an independent test set, essentially. So this is our attempt to try and get more of an independent test set, if that makes sense.
I hope it is. For me, yeah, I think so. Okay, talking about spatial correlations. So we noticed you use spatial lags as one of the variables. So does the spatial lag you mentioned have also a temporal component? I guess the idea would be, can we, if there is distance effects, but across times?
Yeah. No, good. It does. So right now we're using, it's a spatial temporal lag. So it's basically the 1 year lag of the surrounding deforestation. And basically that was our cheap way of trying to get some measures of distance to forest edge, knowing that forest edge is somewhat porous in some of the setting. So but basically the idea that, if you're seeing a fair bit of deforestation nearby, you're much more likely to get deforestation. So yeah, picking up this diffusion process. And it did seem to help. There's right now the area, our definition of neighbors is, we're using about a 50K radius. That's probably bigger than optimal. There's a lot of tweaking we have yet to do on that, but yeah.
Thank you. Kathy, I have a series of questions on comparing your RNN model. Does it make more sense to compare to regression tree, random forest model rather than OLS? And a lot of different questions about all the different model you can compare to. So can you?
No, that's a great, yeah, absolutely. And so in an earlier piece of work where in the state of Michoacan in Mexico, we actually did sort of a comparison of random forest to a neural network to sort of a spatial econometric model. We sort of did a bunch of threw a bunch of models at the wall. And the neural network was outperforming them. So that's kind of why we decided to run with that one. And you're right, we could totally compare that to XGBoost in any of the or any of the regression tree kinds of models here, which would be interesting. One of the reasons why we could do that easily for the cross-section. For the time using the panel regression trees, including like random forest, my understanding is they still don't play particularly well with time series data, partially because they can be picking sort of information from the future and using it to try and predict the past. So whereas the nice thing about particularly the recurrent neural network, but also true with like the 3D CNN models, is they sort of have a better structure to take time and space into account in a way that's sort of logical in terms of treating time as moving in one direction, if that makes sense.
I hope it will make sense for the people asking the question. And closing a little bit these sections, did you check the sensitivity of the model regarding the number of hidden layers, nodes, and the type of activation function? You show up all the different curves.
Yes.
Is that something? Can you elaborate on that?
No, thank you. And so yeah, we did. With regards to the number of layers, we tried to keep it sort of as parsimonious as possible, in general, in terms of number of hidden layers and nodes. So that's kind of what we were using the validation set for, essentially.
Thank you, Kathy. So now I have a couple of questions of outcomes. I will group them. At the beginning, you say that potentially you can have several outcomes. So people are asking, once you have your model, your neural network, can you add fire as an outcome, or can you also, and a similar question asked if you can predict population sizes of species in different locations. So
Yeah,
let-
no, fires that, I mean, in as much as those fires are sort of big enough to be picked up by VERS or something like that, we actually did do this also in Mexico, which was, yeah, it was interesting anyway. And so, yeah, one could definitely use fires as an outcome, and that would be interesting. Thanks, Sheila. I think that was your question. If one was developing a model to predict sort of multiple outcomes, that would be a neat one to layer in, I think.
So you will need, yeah, the data to be detectable, to have a data source to train the model, and to have a model itself explaining the relationship. I mean, do you need the relationship between the second outcome and the first outcome, or just between the input variables? And
you don't even actually. They could be completely independent, but if in as much as they aren't, that'll help strengthen the model. To the question about the population, species population thing, the conceivably, sure. The real trick would be having good training data, obviously. And that's, I mean, this is the downside of these models, is that for them to work well, they need lots of data. I mean, there's a number of machine learning models that can be trained with a lot smaller data size, but not these guys.
excellent. All right, so now let's enter the more important session, I would say. That's part where we made the connection more explicitly with the impact evaluation field.
Right.
And we have an excellent question asking, is there a difference between predicting counterfactual outcomes and estimating counterfactual outcomes? And if they are different, why would I prefer one over the other when doing an impact evaluation? Easy one, right?
That's a really good question. I mean, quick answer is not. Is there a difference? Not really. The way we've set up this model, partially because we wanted to set it up for both possible counterfactual stuff, but also for to be able to forecast, if you like, future deforestation. We sort of set it up where we're sort of holding ourselves, where we're not training it on data that's concurrent with deforestation. We're only training it on sort of earlier data to forecast deforestation. If we were using it purely for counterfactual estimation, we wouldn't need to do that. We could actually probably get slightly better fits by including things like potential agricultural revenue from that specific year to understand how well did a protected area mitigate against, say, a price jump in the price of soybeans or something like that. Whereas, yeah, we're sort of tying one hand behind our back a little bit in this case. We're trying to do forecasting, but yeah.
All right, and so people are asking if you made an assessment comparing the outcome of this type of model to see if you have different findings than those of more, let's say, traditional counterfactual models. I mean, have you made a kind of comparison? Can you?
Yeah, no, I mean, so far just really graphically. So I mean, we've
and just the sum totals. It's sort of interesting. We're actually doing a much better job of also getting the total deforestation right versus the OLS models, which were well, interestingly, on the cross-sectional version, we're massively underestimating deforestation, and then when we did the panel model, it was massively overestimating deforestation. So that there is in part of this is just the nature of the targets or the dependent variable that we're trying to use, because as everybody knows, right, we have lots of zeros. Trying to get sort of the functional form that works well here ends up being kind of a bit of a pain. And that ends up sort of, I think, meaning that our OLS models aren't working super well. We definitely do notice, I mean, even just from those maps, right, we're picking up deforestation in places that in the neural network that we're not picking it up in the OLS models. So spatially, we're definitely seeing things work better. But yeah, there's lots more to be done.
And thank you for presenting a preliminary and preliminary findings and be open a bit about many things you still have to test.
Well, appreciate everybody's forbearance. Seeing stuff hot off the press, but yeah, no, it's
sometimes it's good to see how the sausage is made before you come with a super consolidated model. Going back to the neural network, someone asked if the model can classify deforestation between different biomes. I mean, you talk a lot about the spatial diffusion, everything. So I think people want.
Yes, and no, this is exactly one of the reasons why we wanted to go this route, is that you would expect there to be lots of heterogeneity by biome, et cetera. And so we again, we've done this with a cross-sectional model, but not the recurrent neural network yet. And it does seem to be picking up, like in different sort of at least agroecological zones, it seems to be doing a better job of capturing that kind of heterogeneity versus the sort of standard OLS model. Just again, because it can interact that with everything. As opposed to, again, if you were just running this as a regression, you might interact your agroecological zones with one or two features, but not everything, and not in all sorts of increasingly nonlinear ways.
Interesting. And so we are moving slowly toward the conclusions. I wonder if you have ideas of applications, and especially beyond academic research. I don't know if you want to.
Yeah. So definitely, and I mean, obviously, there's a number of other folks working in this space to develop these kinds of models for predicting, basically trying to predict deforestation threat. To then use that to give a sense of some measure of additionality of credits, right? And that this would be a model that you could use for that kind of thing. We're going about things a little bit differently because we're trying to, most of those are very geographically based, and we're trying to include a little bit more economic drivers in there, as well as, again, a bit more of this kind of forecasting framework. But anyway, there's a lot of really cool work that's already done there, and this could be, hopefully add into that. The other places that, I mean, just if one has a forecast of where deforestation is likely to happen in the next 5 years, it also could be used for targeting of interventions. And for me, that's honestly was one of the places that got us interested to begin with, is we want to know that just for its own sake, along with the sort of counterfactual pieces. And again, that it could be as simple, not as simple, but I mean, you could even use that to try and direct monitoring, for example.
Interesting. And the last question, it's more a reflection. If you have any advices for people who are at the beginning or in the middle of their learning journey, I mean, how can they quickly be up to speed with these fancy models, or what would you suggest with someone who have a beginner understanding of many of these things and they want to reach your level?
Yeah, no. So forgive the shameless self-promotion. We have a review paper that's sort of talking about applications of machine learning in sort of some of these spaces, if anybody's interested. And that was mostly our attempt as people coming from more of an econometrics mindset to try and wrap our heads around how is machine learning different. So if for folks for whom that is useful, yeah, please, I'm more than happy to send it your way. What I find fascinating is working with people, particularly coming from the remote sensing community, who are using a bunch of machine learning tools, but mostly for classification. But therefore, they're kind of already quite comfortable with the tools, but haven't thought about using them in the kinds of ways that we might for causal analysis. And I think that's so. along with learning some Python and just a little bit about machine learning generally, sort of having some of those conversations with people kind of more on the
computer science side and the remote sensing side have been places where, let's put it this way, I've been learning loads. Just because in part of it's just sort of to both better understand how we're coming at these problems, and then to try and understand how we can put those two approaches together in a way that hopefully makes sense.
Fantastic, Kathy. A lot of work to do, but plenty of potential successful collaboration there.
Oh yeah.
So with that, we are closing the Q&A, and the mic is back to you, Sheila.
Wonderful. Well, thank you, Kathy. That was great. And thank you for the robust conversation moderated by Seb. I want to preview our next speaker. We are lucky to have Jo Peary from the International Fund for Agricultural Development. She'll be speaking on the first Tuesday of December, so that's December 5th. And I also want to thank everyone who makes this possible, the board of the working group, Rachel and Seb for moderating and hosting along with me, and of course, all of you for showing up and participating and asking your important questions. So thank you for now, and we hope to see you next month in December.